In this lecture of design principles of concrete structures, I will discuss about T and L beams. Here is the T beam, here is the L beam. However, most of construction of beams in which we cast beams and slabs monolithically means beam reinforcement entered into the slab. So in these types of beams, major part of the beam which are connected to the slab act as in compression, means generate the compressive force, which give us benefit of designing lightweight beams. So I will discuss about how to analyze and design of T and L beams in this lecture. T and L beams. With the exception of precast systems, reinforced concrete floors, roofs, decks, etc. are almost kept monolithic. Second, beam stirrups and means beams shear ties and bent bars extend up into the slab. Means if there are bent up bars, then bent up bars will enter into the slab also, because the hanger bars places in the slab portion. Similarly, stirrups or ties also entered into the slab. It is evident that therefore the part of the slab will act with the upper part of the beam to resist longitudinal compressions. Means if we place a neutral axis here, then the above part of the portion of the slab will act as an compression. You can see here the initial shape, here the bending shape of the T-beam. Okay, above the neutral axis, all of the portion of the T-beam will act as a compression force. Okay, we do not most of the time, even most of the time, we do not need the compression reinforcement, just like we did in the doubly reinforced beam. So in this T-beam, only the tension steel comes. The slab forms the beam flange, the upper part of this T-beam, that is beam flange, and the lower part of the slab, below the slab, the beam, that is the projected part, that is the web. The slab forms the beam flange, while a part of the beam projecting below of the slab forms is called the web or the stem. This part is called the web or the stem, and this part is called the beam flange. Here is the T beam and L beam. B is the effective width or the flange width. For L beam, that most of the time that are our edge beams. So that is the effective width, height of flange or the thickness of flange, that is the effective depth from the neutral from the center of the steel to the top of the concrete. Now, how to calculate the effective depth, effective width of this T beam or the effective width of L beam? That is the criteria given by ACI code. Effective width of T and L beams. This criteria for T beam, and in the next slide I will show for the L beam. How much B will be count in the analysis and design, that is effective width will be minimum of the following. Means we will get three values and the minimum of three values will be the effective width. First criteria is L by 4, means the span of the beam divided by 4. Second criteria, 16 times HF, means 60 times height of flange plus BW, width of the web. The third criteria, BW, width of the web plus half clear spacing of the beam on both sides, means that is the slab will be projecting from the toward this side, and the slab will also project it toward the left side. So we will calculate the span length on this side and this side. We will take the half side from this side and half side from this side of the slab, and this portion will be count as B. Effective width for the L beams will be minimum of the following. First, L by 12. Second criteria, 6 times height of the flange or thickness of flange plus PW. The third criteria is the width of the web plus spacing on one side of the of this span. Okay, for example, in the L beam, only the spacing will become only on the one side, not on the other side. For T beam, for that will be on the both side. Okay, note only above discussion, this discussion for L and T beam is different for isolated or with precast units of T and L beam. Means this effective width criteria for T and L beams will be different for isolated units also of precast. Other discussion is same, means analysis and design of T and L beam is same. Now cases for the analysis of the T beam. First of all, inverted T-beam. Most of the time architect recommend that I do not want to see, or I do not give you permission to the structural engineer that do not project the beams at the bottom of the slab. I want the plain bottom of the roof. So in that case, structural engineer provide the beam on the above side, and this type of beam is called inverted T-beam. Okay, most of the time this inverted T-beam is needed in the design. In that case, when there will be bending behavior below the neutral axis, for example at the center of the beam, below the neutral axis all the part of the concrete will be in tension, and above the neutral axis all the part of the concrete will be in the compression. And in the ultimate strength design we ignore the concrete below the neutral axis. If we ignore the concrete below the neutral axis, then we can design this beam as a rectangular beam, because we have ignored this concrete below and we have to consider only the concrete that is in compression. Similarly, here when there is a negative moment, for example here is a fixed-ended beam. At the center there will be a positive moment, and at the spot there will be negative moment. When at the center there will be positive moment, then at the in the beam at top there will be compression, at bottom there will be tension due to the positive bending moment. At the spot the condition will be different. At the top there will be tension, and at the bottom there will be compression. Okay, so that is the condition of the negative moment. When the due to the negative moment, above the neutral axis that will be in tension, below the neutral axis that will be in compression. In that case also, so the beam will act as a rectangular section, because we will ignore the concrete in the tension side and we consider on the concrete in the compression side. So we will also design in the both cases of inverted T and negative movement. In both of the above cases, beam can be designed as a rectangular beam. Case 2, flange in the compression and neutral axis lies within the flange. For example, when we perform the calculations and the neutral axis depth, okay, do not lie in the web, lie in the flange, in the beam flange. Okay, in that case the beam is also designed as a rectangular beam. Why? Below the neutral axis we have to ignore the concrete, and we will consider the concrete in the compression only. So this beam will be designed as a rectangular beam. Beam can be designed as a rectangular beam of total width B and effective depth D. Okay, these conditions met when the neutral axis lies within the flange. Third case, case 3, flange is in compression. And neutral axis lies outside of the flange. Now you can see the neutral axis lies outside of the flange. Beam has to be designed as T-beam. Separate expressions are to be developed for analysis and design. Means for third case, we have to now develop the expressions for the analysis and design. Above the neutral axis in the T-beam, all the part is in the compression, and the center part portion we have divided just by making the nomenclature. The web part, that is CW, and the left and right part, the remaining part will be CF, and the half part CF will be here, flange part and half part CF will be here. Means the total compression will be CW plus CF, and that is the HF, thickness of the flange. That is the strain diagram. At the top of concrete, that will be 0.003, and at the bottom strain in steel. And that is the Whitney stress block diagram. We have to convert the concrete stress into equivalent stress block diagram for the analysis. Okay, here is the neutral axis depth, that is C, and that is the equivalent width of the stress block diagram, that is A, that is the Whitney's depth. Okay, and the concrete stress, that is a 0.85 FC prime. And in this figure you can see there are two components, CW and CF. Okay, so that's why CF, CW, and the third part is the steel, that is T. Now the lever arm, you can see when we convert C into A, we basically multiply with beta 1 to get the A. A is equal to beta 1 C. So we get the A, for example here CW. CW is same just like a singly reinforced beam. Okay, CW, the lever arm is D minus A by 2, but the CF part, to convert in the equivalent stress block diagram, we have to multiply HF into beta 1. Okay, so this thickness will be, when we convert into equivalent stress block diagram, the flange thickness will be beta 1 HF. So for lever arm, the CF will be act at the center of the flange, so that's why B1 HF divided by 2 to take this height. So the lever arm for the CF will be D minus B1 HF by 2. Here D minus B1 HF by 2. Here is the description. CW, compression developed in the web, that is equal to 0.85 FC prime BA. This is the same formula, just only the difference is BW, width of the web. CF in the compression developed in the overhang portion. Okay, so in the center we have already included. So the effective width of the flange, that is B. So compression developed in the overhang portion will be calculated as 0.FC prime B into A. B is B minus BW, because BW is already counted in the CW. So width is B minus BW and height is beta 1 HF. Okay, this is the area of this CF. So total compression will be CW plus CF, and the total tension will be, to counter these two forces CW and CF, the net steel will be provided in the tension side. So total steel will be TW plus TF. TW tension to balance CW and TF tension to balance CF. Okay, we have to provide the total steel to balance these two forces to make a equilibrium. It is convenient to divide total steel into two parts, just like I have shown in the TF and TW. The first part, that is ASF, that will be in the flange, and as the result of CF, represent the steel area which, when stress to Fy, means stress to yield, is required to balance the longitudinal compressive force in the overhang portion of the flange that are stressed uniformly at 0.85 FC prime. I will explain this sentence already here. That TW will be used to balance CW, TF will be used to balance CF. So here is saying the TF will result the steel ASF, and TW will result the AW. So ASF will be provided to balance CF, and the remaining the remaining steel, total steel minus ASF will be web steel at a stress Fy is balanced by the compression in the rectangular portion web above the neutral axis. Means the half part of the steel will be balanced by Cf and half part of the steel will be balanced by Cw. Here Tf is equal to ASF Fs and the Tw will be equal to ASW Fs. So ASW will be total steel minus ASF. Okay, that will be remaining steel ASW. Majority of T and L beam are under reinforced, mean they comes under the category of tension control. Why? Because of the large portion of the compressive concrete area provided in the flange. Okay, so concrete is due to large portion of compressive force, concrete do not break, so only the tension will go into the yielding. For equilibrium, on the balancing of horizontal forces, TF, how balancing the horizontal forces? Here, when we provide this summation F in the horizontal, means this horizontal forces will be balanced by this horizontal forces. Means left forces will be balanced by right forces. So TF will be balanced by CF, and similarly TW will balance CW. First of all, TF will balance CF. So TF is equal to ASF Fy and CF is equal to 0.85 Fc prime B minus BW into beta 1 HF. Fy will be divided on the other side and we will get the steel required for the flange portion. For the weft portion, that is the remaining steel, total steel minus flange steel multiply with Fy. Cw will be 0.85 Fc prime Bwa and divide this portion by taking on the other side and get the value of A. And to get the neutral axis depth, we divide the A with beta 1, we will get C. If C greater than height of the or thickness of the flange, means neutral axis lies outside of the flange. Okay, this is case for 3. Flexural capacity. How to calculate the flexural capacity from compression side? We can use any couple C into LA, means force into compressive force into lever arm or tension force into lever arm. So this case is for the formula for compression side. We can use either side, both sides are okay. First, from compression side, moment capacity will be MNF plus MNW, mean moment capacity by flange side, moment capacity from the web side. So that is force into lever arm, that is the compressive force in the flange into lever arm, compressive force into in the web into the lever arm. So into the web, that is D minus A by 2, and in the flange, that is D minus B1 HF by 2. CF value is already calculated as 0.85 Fc prime B minus BW into beta 1 HF, that is lever arm, and for CW 0.85 Fc prime BWA. Now for tension side, now from tension side, MNF and MNW, that is TF and TW. TF is equal to ASF Fy and TW is equal to AS minus ASF into Fy. Okay, and here is a simple nomenclature for the steel ratio. Rho W, now you can see only the steel will be provided in the web only. Okay, so the total steel in the web, that is the AS over BWD, total tension steel area, all steel will be in the web. Rho F, that is the area of steel required to balance in the flange portion, ASF divided by BWT. Rho balance steel ratio for singly reinforced rectangular section. If that is written rho W over max, that is the maximum steel ratio for T-beam. Simple rho max, maximum steel ratio for singly reinforced section, that is the nomenclature. Now for equilibrium, longitudinal equilibrium means total tension will be balanced by Cw plus Cf. I have just put it the values. T is the total steel As into Fy, and Cw is 0.85 Fc prime Bwa, and Tf is equal to Asf Fy. Now divide the whole part with Fy Bwd. Okay, when you divide the whole part, Fy will be cancelled out, there will be remain Bwd. Similarly here, this new expression, okay, when you will cancel out, you will get this expression. For longitudinal equilibrium and for the tension control, strain S when equal to 0.005, we get the A value beta 1 3 by 8 into D to ensure the tension control. So I have put it the values here in the place of A, okay, to get the rho maximum, that is all the part is same. Okay, we have divided, after dividing this area of ratio of steel, that is the rho W, to get the rho maximum. Okay, we will just put the value of A for the tension control for the maximum steel ratio. So here in the place of A, I have put it the values 3 by 8 beta 1 D. D will be cancelled out. The remaining part will be 0.85 beta 1 3 by 8 Fc prime over Fy. This is the same for singly reinforced beam rho max. Only the difference is ASF over BWD, that is rho F. So that's how rho W max calculated for T beam. If our rho W means our steel ratio in the web is less than or equal to rho W max, tension control will be section, and if the rho W is greater than the rho W max, so then the section will be transition or the compression control. And then we calculate the corresponding phi factor and calculate the capacity of the beam. So now I will show the analysis example. So how to perform the analysis of the T and L beam.